symmetric differences, and then look at the laws of algebra of sets. Set difference, set difference, and symmetric difference. Let's consider two sets. Let A and B be two sets. Then the symmetric difference, then the relative difference, we say relative difference of A and B, or set difference of A and B, written as, so we write this as A set minus B. So we'll pronounce it what? Pronounced A minus B. This is how we say A minus B. So this is defined as the set of all elements in A, the set of all elements in A, as in a set A, which are not in B. And this is defined as some authors write A minus B, and some write just A set minus B. Just write set minus B. So this is defined as the set of all x such that x is in A and x is not in B. So this is what we term as the set difference, or the relative difference of A and B. So now the symmetric difference, the symmetric difference of two sets, symmetric difference of two sets, A and B, is the set of all elements, is the set of all elements that are in A, and B, but not both. So this is the set of all elements in A and the set of all elements in B, but not in their intersection. And this is defined as, so this, the symmetric difference of A and B is written as A, B, and this is defined as the set of all elements in A. So this is defined as set of all elements in A minus B union the set of all elements in B minus A. O, you define it as the set of all elements in A union B, and then set minus A intersection B. Unite the elements and then remove their intersection. So this is what we call the symmetric difference. So it's now time to take an example that will discuss this issue in detail. Example. So from this example, we let A equal to the set containing A, B, C, X, and then B we define as A, B, X, C, D, E, and Z. So what is A minus B? We are now asked to find A minus B and the symmetric difference of A and B. This is the solution. So we start with A set minus B, and this is equal to, so we know the definition of the set difference or the relative difference of A and B. So we just collect the elements of A and then remove the elements of B. So what is the element of A? Elements of A start with small a, so it's here, so we will not write it. Small b is here, we will not write it. Small c is here, we will not write it. And then x is here, we will not write it. So the symmetric difference of this set is empty. I mean, the relative difference of this set is empty, meaning A is a proper subset of B, and that is why their symmetric difference, their relative difference remain empty. Now, secondly, we say, okay, let's discuss A plus B. This is equal to the set containing. So we add all the elements of A and B, we unite the elements, and then doing away with their intersection. So their intersection is this, B, C, X. So this is their intersection. So what is the remaining elements in A? The remaining elements in A is empty. There is nothing in the set A after taking the symmetric difference. So empty union the remaining elements. So this is D, E, and then Z. That is all. And this is what we have as the symmetric difference of A and B. Now another example. This is example 1, because this is example 2. If A is equals to, so if A is equals to, N is equals to 1, 2, 3, the set of all natural numbers. Of course, we don't count 0 here. We are taking a situation where 0 is not included. So, and let K just be some set containing 1, 2, and then 3, 5, 6. Find N set minus K, and then N K. So this is the relative difference between N and K, and this is the symmetric difference of N and K. So solution. So now the relative difference of n and k will be n set minus k, and this will be, so all the elements of n will remove the elements of k. So 1, 2, 3, so 4 is here, so we start from 4. 5 is here, will not include it. 6 is here, will not include. So we'll start from 7, 8, because it's an infinite set, so the list will continue. All the elements that are in K have been removed, and this set will be infinite. And so the relative difference will still be infinite. So let's look at the symmetric difference. N difference K, this is equal to, so we take the union of the two sets and then remove their intersection. So 1, 2, 3, 5, 6. So we start from 4, 7, 8, and then it will continue. So in this case, you see that in this example, n minus k is equals to this. I mean, the relative difference is equal to the symmetric difference in this situation. So to begin with the laws of algebra of sets, let's start with the idempotent law. 1. The idempotent law. Idempotent law. Idempotent law. And this law states that A union A is equal to A. Similarly, you have A intersection A is equals to A for all set A. Every set, its intersection with itself is equal to itself. And the union of itself in two places gives back the set itself. And that is what we refer to as the idempotent law. So secondly, let's take the involution law of involution. Involution. And this involution is saying that if you have A complement and then complement, the answer is equal to A. That is the involution law. The complement of a complement is the set itself. And then 3, let's take the commutative law. Commutative law. I don't have to write the law because the law is already here. So we know we are talking about laws. So the commutative law. So I have A union B. This is equals to B union A for all sets. If you have the union of two sets, it doesn't matter which set comes first. And similarly, if you have the intersection of two sets, A and B, it doesn't matter whether you start intersecting with A or with B. So if A and B are two subsets or sets, then the union of A and B, you can say it as A union B, or you state it as B union A. Likewise, their intersection can be A intersection B or B intersection A, it doesn't matter. So that is the commutative law. And we also have the associative law. We have the associative law, and this associative law is saying if you have A union B, this and then union C, this is the same thing as saying A union B and then union C. Meaning it doesn't matter if you have a union of three sets, you either start uniting the first two, or you unite the last two, then intersection, if you have A intersection B intersection C, you can start A intersection B, then intersection C. Or you start A intersection B intersection C. You can start with B intersection C, then you come A intersection, the intersection here. So now we are supposed to take the identity law. And the identity law states that if you have a set A and you have its universal set, so union, A is a subset of a universal set, union the universal set U. So this gives the universal set itself. So the union of a subset with its universal set is the subset, so is the universal set. And if you have A union the empty set, the answer is what? Is A itself. So observe that in this union, A is the identity, and in this union, the empty set is the identity. So let's talk about the other part, the dual part. Meaning you have A intersection its universal set. The answer is what? The answer is A. Because the intersection between a subset and its universal set is the subset itself. And then if you have a subset A intersection the empty set, then it is the empty set. Because every empty set is a subset of every set. So the intersection of every set you think is the empty set itself. Every set you can think of, then the empty set is the intersection of the set with empty set, because empty set is a subset of every set. And so here, the identity is the universal set. The identity here is A. A is the identity. So now we are going to take the De Morgan's law. We are taking associative law. Let's take the De Morgan's law. De Morgan's law. So the De Morgan's law states that if you have A union B complement, so this is equal to A complement intersection B complement. And the dual part is saying if you have A intersection B complement, the answer is A complement union B complement. That is the De Morgan's law. And finally, let's take the complement law. The complement law. Complement law. Let's take the empty set. The complement of the empty set is what? Is the universal set itself. That is the complement of the empty set. And now, if you take the complement of the universal set, let me place it here. You take the complement of the universal set, that is the empty set. The distributive law. Distributive law. That is, if you have A union B intersection C, this is equal to A union B intersection A union C. You see, the union now is distributed over intersection. And the dual is, you have A intersection B union C. This is the same thing as A intersection B union A intersection C. Now, its intersection is distributed over union.